In Section 4 of Unit 3, we're going to take a look at statements and quantifiers. Statements, negation, symbols, quantifiers, sets of numbers, and let's get started. So, first thing in your notes, what is a statement? A statement is defined as a declarative sentence that is either true or false, but not both at the same time. That is, simultaneously. Now, often we have what are called compound statements. This is background. You want to get good definitions. A compound statement may be formed by combining two or more statements. The statements making up the compound statements are called the component statements. And there are connectives. These are words that tie the two statements together. Examples of connectives, and I'll underline these for you. You want to have these sort of highlighted or something. And, or, not. If, then something in the middle, then. So these are four that are often used. Now for our first example, 1 pp, decide whether each statement is compound. If Amanda said it, then it must be true. Well, there is a first statement, and it's showing the connective if then. So this is a compound statement. In letter B, the gun was made by Smith & Wesson. Here the connective N just connects two people or two names of a company. So this is not a compound statement. Now, another key word is negation. The sentence, Max has a valuable card, is a statement. The negation of this statement is Max does not have a valuable card. The negation of a true statement is false, and the negation of a false statement is true. Now, an example of this in everyday English or common English, just to give you some background, and this isn't very good English, but it's what we want to say here. I got no money. Well, does this person have money, according to this statement? And the answer is no. Now, how about if I put another negative in there? I ain't. Not sure that's a word or not, but we hear it. I ain't got no money. Now, does this person have money? Think about it. And the answer is yes. He has money, or she has money. And you might say, wait a minute. I ain't got no money. It's in songs. And that's strange. So what's going on here? Well, here, this is in the negative, no money. So the negative is there, no money. But the word ain't is like am not, or another negative. So you are negating that you have no money, which implies that you do have money. So the negation of what would be a no makes it a yes. A little bit of words and syntax and things like that. Let's go on. And a quick review of inequality symbols as we look at these, and we have had these before. In symbolism, A is less than B. A is greater than B. A is less than or equal to B. A is greater than or equal to B. Now, we had this in an earlier unit where in order for this to be true, it has to have that A is less than B. Or this to be true, A is greater than B. But we said when it's in this symbol, A is less than B, that could be true. And also, another variation that this would be true is if A equaled B. Here, only one part of it needed to be true. And the same here. So, in symbolism, we need to reflect on this for a moment as we go into our next slide. They want you, for example, to PP, and be sure you are writing these examples down. That helps you to reference the work in your lecture notebook. It says, give a negation of each inequality, and then do not use the slash. So here we're talking about that sometimes we say this is equal, and then this is not equal. That's the slash they're referring to. So we're not going to use that. Now, what would be the negation of P is less than 3? Well, it would be P is greater or equal to 3. Now you might say, how about just greater than without the equal? And then you would be leaving out the equal that would negate this. So it's important that you put both parts. And here in letter B, 3x minus 2y, now they're saying is greater or equal to 12. So to negate this, all we have to put in is less than 12. So note the negations here. Again, if you see something like this, you have the reference for it in your notes. You would just have to study to be sure you use it correctly here. We went back one slide for some reason, and there are the answers again. Okay, now you will probably need to write this in your booklet. So this is to be included in your notes. Symbols now, and these are symbols that are going to be used in what we call symbolic logic. Now, we have the connective, and the symbol for that word in symbolic logic is the caret. The connective or is a symbol, the inverted caret. Now, for the connective not something, or as we will see here, the negation, is a symbol that looks like this. Now, for some reason, when in some of the PowerPoint slides, when you see the negation, they're like putting a box or something. I'm not sure what that reference is to, but this is the symbol for negation. Now, the type of statement that the and is related to with the caret symbol is the conjunction. And just for a little review, in mathematics, if we have a conjunction, it might have started off looking like so, if we were to graph it, and looking like so. But because of the connective word and, it's just the part where they overlap or intersect. That is the conjunction. So the conjunction looks like this. Let me just put it here. This would be the conjunction. Now the disjunction, if you were to graph it, it would look like this. With a line this way and a line this way. Sort of like disconnected. But here we have the word or, and the disjunction, again, in its graphic form would appear like so. Now, just to tie this up with things we did a little earlier, and in previous units, the word and, if you recall, was the symbol of intersection. The word or was the symbol of union. And you may note that the symbol in symbolic logic, here is the caret. It sort of opens up down, where this is a U, this is more of a V pointed shape. The union, the or, has this line right here. So again, some background and some things you'll need to know for symbols and definitions and things. Now here, in this example, and this should be considered example 3, we're going to start converting from English into symbolic logic, where we're going to say, let the letter P represent it is raining. So this is going to be P, this statement. And let Q represent it is March. So this is going to be statement Q here. Write each symbolic statement in words. So what does this say? Well, it's just P, and it's going to be it is raining. Now what does this symbol, the inverted caret? And it's the word or. And then we write Q. It is March. And that is for statement 1. We've taken it with our what P and Q represents. These are often used in symbolic logic, these letters. And then looking at its symbolism, convert it to a statement. This would be a compound statement with the first component and the second component and the symbol or. Now for letter B, and you have to be careful because again that box shows up. I tried to get rid of it, I couldn't. So the red mark is the symbol for negation. It says negate this. So as we write the negation of this, it is not the case that, and then our P statement, it is raining. Now, what connective, what word do we put here? Think about it. And if you said and, that is correct. And then the Q statement, it is March. So again, our first work in translating from symbols into words, where P and Q, again as we said, often used in symbolic logic, and then understanding the symbolism. And we'll take a look. And there we are. And there we go. Now, we also want to build up vocabulary by looking at what we call quantifiers. Words like all, each, every, no or none are called universal quantifiers, quantity. That should be written up in your notes. While words and phrases such as some, there exist, and for at least one, are called, where everything is not included here, existential quantifiers. So for a quiz question, I might ask, what are some universal quantifiers? Or I might ask the same of existential quantifiers. Or I might use the words and say, what kind of quantifiers are they? And similar to this one. Now, quantifiers are used extensively in mathematics to indicate how many cases of a particular situation exist. And again, a little chart that might be very useful. Statement is all do, and the negation some do not. The statement some do, the negation none do. Now here there are little fine lines. Notice you might say here all do for the statement and then none do. But the negation is not none do, but some do not. Keep that in mind. Okay, now here we get to apply what we've just had. This is example 4, as you put this in your notes, again, you're using this to delineate where things are, forming negation of quantified statements, that is quantity. Statement A. Some cats have fleas. What would you put down for that? B. Some cats do not have fleas. What would you use for that? And C. No cats have fleas. Now, as you do your homework and on the test, you'll see that often these statements are given in multiple choice. So you have to read through the list to pick out the one that best matches. And here are the answers. So if you had something like this, then you're correct. So for some, we're going to use no. For some here, we're going to use all. And for no, we're going to use some. So a little subtlety of statements. Now, this is something we already have, sets of numbers, a number of times, and we're assuming you know these. And looking in our book, I don't see I've written this again, but it's in your notes and in your booklet. So these are sets of numbers. Remember, the synonym for natural numbers are counting numbers. And then they're defining them as we go on. Now, here we want in example 5 to decide whether the statements are true or false. And as we read them, every integer is a natural number. Now, every is a universal quantifier. Is every integer a natural number? No, there are lots of integers that are not natural numbers. So this is false. And again, you want to know why to be able to defend it. There exists a whole number, and this is a set of numbers, that is not a natural or counting number. Well, remember, when we were defining sets, counting numbers are 1, 2, 3, on into infinity, while whole numbers were 0, 1, 2, 3. The only addition to natural numbers were the, for some reason my pen is going wild, is the 0. So this next one here would be true, because there is this 0 that is a whole number, but not natural numbers. All right, let's go on here. And there are the answers. And they're giving you an example for letter A as well. Again, if you just find one that makes it untrue, since they've used a universal, the universal every, then that is one example that shows it's not every, that makes it false. We're now going to look at examples from our textbook that I've written up in your booklet. You want to decide whether these are compound statements or so. So as we look at statement A, he wrote sonnets, and there's our connective, poems exhibiting this. Yes, this is a compound statement. You can pay me now, or your connective, you can pay me later. Yes. If he said it, then, here this is an if-then, it must be true. That's compound. My pistol was made by Smith and, here it's just to connect two words, not statements. So this is not a compound. And we had that one in our PowerPoint as well. Okay. And there they are. Again, pause it. And if you have a textbook, of course, these should be there. Now, we want to form negations of these statements. And I would suggest you write it out. What do you think the negation would be? And then for part B, that city has negation, no mayor. The moon is not, the moon is. That would seem reasonable. And again, we're showing this from our textbook. These are your inequality signs, and here are examples. So give the negation of these. Take a moment. Now here we said it would be x is greater or equal to 9. And here we said 7x plus 11y is only going to be less than 77. So when you start off with just part of the full inequality, then the opposite is to change the direction and to include the equal. If it does have an equal as part of it, you leave the equal out and just reverse the sign. Sort of a shorthand method there. And there we see it. Okay, now here it gets a little more challenging, and I've put the solution with it instead of putting it on two separate things, because you're going to have to look at the symbolism and then come up with a phrase to support it. So let's just look what they have as we take apart the symbols here. P and Q. Now remember, P represents this statement here, and Q represents this statement here. So what connective are we going to use here? This would be an OR. Now here, what are we doing to the P statement? We are negating it. So not this, or no. And this connective here is and. That's the caret. And then just Q is regular. Now for C, this is negating both of these. So it is not the case. And then statement P, and what connective are you going to use here? Or, because that's similar to this one. And then again, it is not the case, because we're negating what's in here, this statement, and then the word and. Once you kind of fiddle with this a little, there are the words. Now, we did these earlier. Again, you want to form negations of quantified statements. Here, some Then the quantifier, as you recall, would be none. Some cats do not have fleas. No cats have fleas. So for A, none, or in this case, no, to make it better English. For B, all cats have fleas. And then the negation of no would be some. And they're giving you this little note here. Avoid all cats have fleas. The negation of no is not all. It's some. So as you do your multiple choice selection of statements in your homework, that's something you'll have to look at carefully. And this is a repeat. And then deciding. There exists a whole number that is not a natural number. We did this one earlier. This is going to be true. And that would be 0. Every integer is a natural number. No, we said -1 is an integer, but it's not a natural number. So this one's false. Every natural number is a rational number. There, the universal quantifier happens to be true, because this would be like a subset of rational numbers. D, there exists an irrational number that is not real. Well, in this case, all irrational numbers are real, so this statement is false. And again, analyzing is part of what you are going to develop as you think of this symbolic logic. And there we see the answers. Pause if you want to read them in more detail. And that would be long enough, so we're going to complete what we've done here.